The modern digital computer is ubiquitous. Because it's penetrated all aspects of our lives, we tend to think that binary electronic computers are the only possible form. However, this wasn't always the case. The first programmable computers proposed by Charles Babbage and others in the 19th century were mechanical devices, and in the early 20th century, analog electronic computers were also popular. And this was the origin of the operational amplifier, or op-amp for short. It was originally designed to be a component in analog computers. The operational part of its name refers to mathematical operations like addition, subtraction, multiplication, and division, and even complex tasks like integration and differentiation. And, as we'll see, the op-amp can do all these functions and more. When analog computers lost out to digital ones, the op-amp proved just too useful to abandon, because being able to perform all these mathematical functions on a signal meant that it was a godsend to signal processing circuitry, particularly for instrumentation systems, and that's where it's still used mainly today. The original op-amps were built from discrete components, but now they are universally available as integrated circuits on a single chip, as described in our last video. So what does an operational amplifier chip do? An op-amp is an amplifier with a very high gain or amplification. In the perfect case, this would be an infinite gain. And it amplifies the difference between two inputs, called the inverting input and the non-inverting input, as shown in the diagram on the screen. In other words, it is a high-gain differential amplifier. Note that the non-inverting input is often labelled with a plus and the inverting one with a minus, but these do not refer to power supplies. They are the input signals. The op-amp requires a separate power supply just like any other amplifier, although this is often left out of a circuit diagram for simplicity. Theoretical op-amps have infinite gain, zero output resistance, and infinite input resistances. However, real ones are not perfect, and so these figures are all finite, and this can affect the op-amp's circuit behavior, as we'll see later on. Real op-amps are made from transistors. The first stage is either a BJT or FET differential amplifier. The next stage, or two, gives simple gain and is a common emitter type circuit, sometimes employing a super beta transistor. Finally, there's usually a push-pull amplifier or buffer at the final stage. The gains of these stages multiply together to give a very large overall gain for the whole circuit. A typical real op-amp is usually packaged in an 8-pin dual inline package as shown on the screen. When op-amps are used, they are usually wired up to some external components which provide feedback. Feedback is where some of the output of a circuit is taken and fed back to the input, as shown on the diagram on the screen. In the next couple of videos, we'll discuss feedback before we have a look at real op-amp circuits.